Okay, hello everyone. So we'll continue from the next part. So we have seen the Butterworth and Chebyshev filter design. Okay, so we know that it's already we already know that this is what we have seen till now. It is the analog filter design. Okay, so now the task is to do the digital filter design, right? So this is all the procedure. So first thing is, here we have to design an analog filter and then we convert that into digital filter. So design the first required analog filter. It may be Butterworth or it may be Chebyshev. So once you get the transfer function of an analog filter, required analog filter, then you can convert that into digital filter. Okay, so this process we call it as S to Z plane mapping, right? S to Z plane mapping. Okay, right. So what is this S to Z plane mapping? Is the transfer function of IIR digital filter can be derived. The transfer function of IIR digital filter can be derived from the transfer function of IIR analog filter using the S to Z plane mapping. So this process is called S to Z plane mapping, analog to digital frequency transformation technique. This is also called as analog to digital frequency transformation technique. Okay, there are two methods here. There are two commonly used methods S to Z plane mapping. So first is bilinear transformation, and the second one is finite backward differentiation method. Okay, finite backward differentiation method. So first we see bilinear transformation method. Okay, so here this you can see the diagram, bilinear transformation method. Okay, so this bilinear transformation method is based on trapezoidal integration rule, trapezoidal rule of integration. Okay, so to derive this transformation equation, I have to consider two analog quantity. That's what you can refer it in the diagram, right? So one is WA of t and one more is YA of t. This is x is YA of t. So this Y of t is WA of t is written as differentiation of, dy of t by dt, first thing, right? Then you take the Laplace on both the sides, you get WA of s, and this becomes s into y of s. So integrating equation 1 both the sides, you get what? This is integration if you write here. So this becomes integration from n minus 1 to n minus 1 t to nt. W of t dt is equals to n minus 1 t to nt dy of t by dt, right? Now the you approximating the left hand side of integration by trapezoidal rule. So this can be written as t by 2 w of n minus 1 t plus w of nt. This is on LHS, left hand side. On the RHS side, w of t is integration from n minus 1 to t to nt. So this can be written as y of nt minus y of n minus 1 t into nt. So here you could see these equations. Okay, so using usual notations, the discrete signal we write it as t by 2 w of n minus 1, okay, into w of n. Okay, right. So likewise here also it is y of n minus yn minus 1. Okay, discrete signals, usual notations for discrete signals. How do you write for discrete signals, right? W of n minus 1 is as it is, W of nt can be as W of n, because this is t is at period there. Okay, right. Same thing over here. So y of nt is nothing but y of n only. T is a period of this thing, right? And y of n minus 1 can be written as y of n minus 1. Okay, right. Now take the z transform on both the sides. This is discrete signals we have written. No? So now take the z transform. So t by 2 z inverse w of z is plus w of z. On the RHS side it is y of z becomes y of n is nothing but y of z. Y of n minus 1 z transform can be written as z inverse into y of z. Same thing both the sides. Taking z transform on both the sides I have written this. Okay, whereas wn minus 1 is, this becomes z inverse w of z. Wn becomes as it is w of z. Here also on the RHS y of n becomes y of z. Y of n minus 1 becomes, if you take the z transform of y of n minus 1, it is z inverse y of z. Okay, so you rearrange this equation. you get w of z is equals to 2 by t into 1 minus z inverse plus 1 by z inverse into yz. So this equation I have written it as 3. So compare this 2 and 3. Okay. So comparing, you can write s is equals to 2 by t 1 minus z inverse divided by 1 plus z inverse. Okay. So this is nothing but the mapping equation. So this is a mapping of s to z plane using bilinear transformation. So if h of s transfer function of analog filter, then transfer function of corresponding digital filter is obtained, right? The h of z is equals to h of s, where s is replaced by 2 by t into 1 minus z inverse divided by 1 plus z inverse. Okay, so this is the mapping equation derivation for bilinear transformation. Now there is one more thing we have to study with respect to bilinear transformation, which is called as warping effect, warping and pre-warping in bilinear transformation. That is what the next topic here. Okay, so here what will happen, the relation between the analog frequency omega and digital frequency omega, right, is non-linear in bilinear transformation. Okay, so due to this non-linearity, the, the, the different bands of the analog filter will be mapped differently in digital filters, leading to a type of distortion called warping effect. Okay, so we'll see that later. So it can be shown that low frequency bands from the analog filter expands in the digital filter and high frequency bands compress in digital filters. So how we'll see this. So we take the bilinear transformation equation, which is already derived, s equals to 2 by t 1 minus z inverse divided by 1 plus z inverse. Substitute s equals to sigma plus j omega, right, and z is equals to e raised to j omega, as it is. Well, substitute here in this, s as this and z as e raised to j omega, right. So if you write this, you simplify this, I mean just rearranging this. So I'll take this common, e raised to minus j omega 2, so e raised to j omega by 2 minus e raised to minus j omega 2, which is again the similar thing, right, and denominator also been adjusted, same thing, 2 by t is kept as it is. So this is arranged in this way because so that you could see the next step, you'll understand. So you can see here, this is sigma plus j omega as it is, 2 by t as it is. This can be written as, okay, so this can be written as